That's usually a big one. Materials and processes has homework. Because if you don't turn it in every week, you turn it in at the end of the year. And grade it on your So a lot of people don't do it until the end of the year. Maybe they forget about it, and then like, so I would just like keep up with that, and then I don't know what you have for Army, and then small leadership. On industrial design lab, definitely, if you have bangers, she asks for a lot of work. But if you have Jonas,
I'm trying to get Jonas.
Yeah.
It's like what I'm trying to do with everything.
Exactly, yeah.
I think I'll just probably wait like 2 days for my advice
Oh,
appointment.
yeah, like it doesn't, I don't think it actually matters. I think it actually just depends on priorities. So I think like it does like seniors, juniors, sophomores and freshmen, like as far as like who gets the class first. But since you guys are all like the same grade, I don't think it really matters. Like I requested Jonas and I got Jonas. Have to be, it'll just be done.
Hi, everyone. Oh. So we've got the start of a new chapter. I think for some of you, this is going to be the last fun that you have this semester. For some of you, this is finally going to be a relief from more subjective parts of math. Can I start just by asking how many people here have taken AP Calculus? Okay. I'm definitely not going to assume that anyone here has taken that. It seems like quite a few of you have. I just want to kind of give you a warning, or I guess I'll start off with a story. When I first started teaching here, I taught Calculus 1, which is going to be what's normally covered for Chapter 3, which is derivatives. I was teaching all engineers. They all got in Virginia Tech, all right, just like all of you did. And I asked them, I said, who here has taken AP Calculus? And almost every single one of them, maybe one or two hadn't taken it, but almost every one of them had taken AP Calculus. And the average grade in that class was still a C, right? We are not going to get in this class, we don't have time to get into anywhere near the level of depth that we do for the engineers. The engineers take basically Chapter 1 over one semester. We call that Calc 1, and then integrals, Chapter 4 would be Calc 2. That's the second semester. So we only have a month and a half. They have, you know, a full year to take it. So we won't get into that level of depth. But if you've taken AP Calculus, I just want you to know that there's going to be certain points where the expectation is going to be a little bit higher than what you've learned in high school, right? I still want to emphasize certain things where you actually understand what's going on rather than just being able to answer a question in there. I'm going to try and address a couple of the bad habits that I think people might have picked up on in AP Calculus. But if you never took it, then you don't have to worry about that. Another kind of important point for this one is, let's say out of the 10 problems that you're given on this upcoming exam, if you feel like you already feel comfortable with something like this, and don't worry if you're not, but Anyone know this one? 3x squared. So you'll see the pattern a little later, but out of the 10 questions, only 1 or 2 of them are going to be something like this, right? Just knowing how to perform derivatives on here is not what I want to focus on, right? For that reason, I'm not going to, you're not going to be allowed to use GeoGebra for this exam because GeoGebra will do these integrals for you. They'll do derivatives for you. And it's not even the most difficult part. Like for those of you that know how to do this, this will be a repeat, but you basically take that 3, put it out in front and subtract 1, right? So, so that's not what I want to focus on is the mechanics of it. That's, you know, really the focus of AP calculus is kind of doing things like that. I want to focus on kind of what these mean so that later on when you see this in your other classes, if you have to take a structures class, I know at least the architecture students, is that any industrial design, do you have to take structures? No? Okay. Well, at least the those of you on the architecture track, you do have to take structures at some point. We're going to be building up to something called the center of mass, which is basically all you do in that class, just over and over again, find the center of mass. But I want to start off just kind of talking about functions and kind of getting you used to the vocabulary that you're going to see in getting used to the vocabulary that you're going to see in these problems here. So the analogy that I like to use for functions, I guess I'll define it first, or at least talk about functions. So what a function does is it takes each input and assigns exactly 1 output. I would sort of think of this as being like a computer program, right? If I feed it some information, it can give me a straightforward answer to any information that I give it. I'm going to use a meat grinder as an example here, or let's say a sausage making machine, right? So here's F, that's my function. The reason I'm using this sausage machine here as an example is just to truly talk about it as in terms of inputs and outputs. If you put pork into this, you're going to get pork sausage out of it. If you put beef into this, you're going to get beef sausage out of it. There's a clear output for every input that you put into it, right? So input goes in, output comes out. So something happens to it, right? The function performs some operation on it. Let's suppose F is a squaring function. Right. So if F is a squaring function, that means whatever I put into that, it's going to square it and spit that squared value out. So if I put 3 into this as my input, the 9 is going to come out. If I put X into this, X squared is going to come out. That's my output, right? It knows what to do with that. Um, so if we want to talk about f being a squaring function, and we don't want to write that sentence on there, another way to write that, and write this nice and big so you can kind of label these parts here. But one way to say that f is a squaring function is to say that f of x is equal to x squared. All right. If we want to say that the operation that happens to any input is that you square it, this is a way to write it. Important features of this, whatever's in the parentheses here, that's your input, right? So I'll maybe even make that even more explicit. I'll say whatever's in the parentheses. Right, whatever's in the parentheses, that is your input. That's what's going into your machine. What comes out of it is whatever happens to that input. So I'm going to call this, this is your output. This side of the equation is instructions for how to produce the output. In this case, you take the input, whatever that happens to be. If it's x, then you take x and square it. So whatever the input is, you square it. So x squared is considered the output. But because f of x is equal to x squared, this is also considered the output. So f of x is, I'll just label it output as well. So those are just two different ways to talk about the output. F of x is the output. If we want instructions on how to find that output, we look at the right side of that equation. F is just the name of the function. That's what we give. That's the name we're giving to that set of instructions. So with that analogy in mind, do an example here. We'll say suppose f of x is equal to x squared. So that's me telling you that suppose you've got a squaring function here. What's f of 3? 9. Good. F of z to the 4th. Yeah, do you add those or do you multiply them? What is z to the 4th? How does that work? What do you do with the 2 and the 4? You multiply those two together. Yeah. So this is so that's yeah, z to the 8th. Good. What about f of x plus 1? I'm going to present you with a couple options here. Think about which one is it. X squared plus 1. Is it x squared plus, I know this is, you know, pretend I picked a more interesting number than 1 here. Which one do you think, A, B, or C? Feeling good with C? I think when I lay it out like this, it's clear that f is a squaring function, but you would be surprised how many people, you know, throughout their math career pick A, right? So again, this is not telling you take any x and turn it into x squared. This is just giving you generic instructions on what to do with an input. F of x, whatever that input is, take that input and square it. Okay. Good. Okay. At some point in your math career, they started off, this maybe happened about, I don't know, 6th grade maybe, they introduced y equals mx plus b, or maybe before that, I don't know. And then at a certain point, when you got into algebra 2, they started saying f of x equals mx plus b, right? And I remember asking a teacher at the time to say, why are we using f of x now? And they said, oh, because y equals f of x. And I said, okay, it doesn't really answer the question, but I just believe you that now we're calling y f of x, right? What's happening there is when we want to use this variable, so this is a function, right? This tells you to multiply your input by m and then add b to it, right? Those are the instructions that I'm giving with that function here. When we say y equals f of x, this phrase is used to graph that function, right? So, so we use this phrase to graph a function. Right, meaning I've got another way to put that phrase there when we say y equals f of x is we've got our x-axis and our y-axis. Saying let's put our inputs on the x-axis because that's what's in the parentheses is our x. So let's put our inputs on the x-axis, and then on this vertical axis that we call y, let's put our outputs here. Again, f of x is our output, right? So that's why we say y equals f of x. And generally when we draw something, so let's say that when we draw this curve here, so let's suppose that f of x is x squared on here, we would say something like, when we talk about this, we talk about this as being the curve y equals f of x. So that refers to on the actual graph, when we draw that curve on the graph, that's different from the equation or anything else, but that is the curve y equals f of x. So when we talk about the curve is increasing or bending or has a concavity, things like that, we're talking about this object y equals f of x. The first thing I wrote up here is a function takes each input and assigns exactly one output. So something like this is fine, right? I've got two inputs, and let's say that they produce the same output of 4. That's fine, right? If I put the input -2 into my function, it knows what to do with that. It can spit out 4. It's not giving me multiple answers. If I've got this point, let's say I've got this point out here, k. So k is my input. And sorry, I should explicitly say what curve I'm drawing here. F of x is equal to x squared. If I've got my input k there, what's the y coordinate of that point going to be? I heard k squared for my y. That's true. What's another way to talk about the y coordinate of that point? So one way is k squared. What's another way to talk about the y coordinate for that? F of k. Yeah. So oftentimes you'll see, I just don't want anybody to panic when you see the coordinates for this point. It's very common to see k, f of k. Let me draw that a little bigger. The coordinates of this point, we could call them k and k squared, but it's really common to see this as being k, and then the y coordinate is f of k. You'll see this phrase all the time in your questions, but just know that they're not talking about anything super fancy. They're just saying k, f of k is on that curve, right? Input and output. There. Okay. So it's okay to have multiple inputs giving the same output. But it's not okay to have multiple outputs for the same input. Let's say that this is the circle centered at the origin with radius 2. So we know this is x squared plus y squared equals 4 is the equation for that. I'm going to show you two ways to determine that this is not a function, or more specifically, that y is not a function of x. One way is a way that you've probably seen before. It's something called the vertical line test. The vertical line test is just a way to quickly, if you have a visual graph like this, you can just do a vertical line, draw a vertical line through it. I'm going to draw one here. So if this is 2, this is 1. And I'm just going to draw a vertical line through it. So notice that this input of 1, I've got 2 potential outputs. That's the vertical line test. So we would say we have one input and it spits out 2 potential outputs, or 2 potential f of x, or 2 potential y values there. So we would say For that reason, y is not a function of x. That's one way to do it. That's called the vertical line test. You do need to know the other way, which is to look at an equation and solve it algebraically. So I'll start with that same. Let's say that you weren't given a graph to go along with this, and let's say we didn't know that this was a circle, or we were given something that we didn't recognize that curve. Algebraically, if we wanted to figure out that we would get two different outputs, we're going to try and solve for y here. So first thing I'm going to do is just move that x squared over to the right-hand side. Some of you already know why I've left a gap here, right? Because whenever I'm going to be a little particular about this. Whenever you take the square root of both sides, you have to put a plus or minus. That's probably how you learned it. When you take the square root of both sides, you have to put a plus or minus in front of the square root on there. Since this is a college level math course, I'm going to get into like why that's the case, because I think it's worth knowing, like understanding really in depth what's going on when you take the square root of something. But the very short and sweet version of it, and I'll just put that here as a note. If you have x squared equals, I guess I'll call it k, then when you solve for x, you need to put a plus or minus out in front of that, right? So you aren't taking the square root of both sides when you do that. You're actually adding information back into that problem. You can choose to write this down or not on here. This is kind of just a little aside that I want to go on. Let's say that you have x squared is equal to 4. If you take the square root of both sides, so this is something totally fine that you can do. Over here, you're going to get 2. But many people mistakenly believe that this is x on there. But actually, this is how you define the absolute value of something, right? Most people think of the absolute value as being, it's the thing that makes it positive, right? But the actual definition is when you take x and square it, that makes it positive. And then when you take the square root of it, the full name of that radical is the positive square root function. So it only takes positive numbers. That's why we don't want to get imaginary values in there. That's why we don't take square roots of negative numbers. But to take it one step further, if I start with x equals -2, and I square both sides, this is also totally fine. So I'm just doing math stuff to this. So these are all true statements, right? But you can see in between this step here and this step here, right? As I go through this process, I've lost some information, right? Like here, I knew that X was -2. Here, all I know is that the absolute value of X is 2, right? So X could be 2, X could be -2. Anyway, weirdly enough, we are not just doing algebra when we take or we're not just performing an operation on both sides of the equation. Anyway, thank you for indulging me with that. I won't talk about it again. But yeah, we could do the same thing that we did here. So the thing to notice is that we have both a positive and a negative result for this. So we can tell already that we've got 2 outputs. But I can show that just as an example. I can select X equals 1. So you can see I get 2 potential Y values. So this is 2 outputs for 1 input. You may be required to see this, or sorry, do this for an equation where you solve it algebraically for y. This tells us that y is not a function of x. If we wanted to show that x is not a function of y, we would solve for x instead. Things worth noting on here. So let's say y squared is equal to x. This is what we should do when we, kind of perform that operation where we essentially take the square root of both sides of that equation. But if I have something like y to the third equals x, you do not have to do that. You can just leave it like that. Yes.
Going back to the other problem, how did you know that x was 1? Or was it like you're just putting an input in?
So the EG means I'm just choosing an example. So that's what I did here at the vertical line test. I just chose 1 for my input.
Okay.
But yeah, I'm just choosing 1 as an example. We can see there's 2 outputs because I've got 2 y values, but yeah, that was just me picking x equals 1. Okay. So I mentioned some bad habits that AP Calculus students have. And I totally understand why they have these bad habits, because if you want to pass an AP Calculus exam, this kind of stuff doesn't matter. In fact, it just kind of gets in the way of learning how to do these problems. But for here, I'm going to be a little particular about the vocabulary that we use. But I'll show you what I would say most people leave an AP Calculus class thinking. In their mind, and this is not everyone, but if you've got your curve here, many people mistakenly will say that this line here is the derivative, right? I'll hear this casually mentioned all the time, where they'll say this line is the derivative, and they know there's some connection, but I really want to talk specifically about what the derivative is, because it's going to be the focus of this whole chapter, but it's not that line, right? So if that's kind of how it exists in your mind, I want to kind of replace that with the actual definition for a derivative. And that starts with talking about defining that line. So here's that curve. Okay. So this thing here, a little later on in, maybe a week from now, I'll start calling this the tangent line, because I'll assume that everybody is on the same page as me and it's unambiguous. But for now, I want to be very particular about it and say this is the line tangent to the curve y equals f of x. So again, that y equals f of x, that's this thing here, right? The actual thing on the graph, that parabola on the graph, is y equals f of x. But this definition is already too loose, because this is the line tangent to the curve y equals f of x. But isn't that also the line tangent to the curve y equals f of x? And many other ones exist there as well. So we want to be specific and say this is the line tangent to the curve y equals f of x at the point. So one way to define this, because we have a function, we can just use the input to define it. We don't have to necessarily know what this point is. We can just say this is the function. We'll call this point A. Sometimes later it'll be called x naught, but let's just call it A for now. All right, at the point is fine. Line tangent to the curve y equals f of x, where x equals A. Right. Now that we have that kind of inner vocabulary, again, later on, I'm just going to refer to everything that I wrote in the orange there as the tangent line, especially if it's unambiguous which one I'm talking about. But the phrase that we can write now to talk about the derivative is I'll write a very specific sentence here. The derivative of the function f evaluated at x equals a is equal to the slope of, and then I'm going to copy everything that I've got here in the orange here. So is equal to the slope of the line tangent to y equals f of x at, sorry, where x equals a. Thankfully, all of this information, it's kind of one of the nice things about math is you can take all of these ideas and just compress it down into something very easy to read, right? So this entire idea where y equals f of x is a curve where you put the outputs of a function on the y-axis and the inputs on the x-axis, and that there's a line that's tangent to that that's defined by a particular input that we call a on there. All of this stuff and the fact that it's the slope of that line and not the line itself. All of this can just be right, just put into this very short language here. All right, so as long as you can interpret those symbols on there and you know how that relates to what I've drawn up here, we can just start using this effective shorthand. So I'll kind of highlight the relevant parts. Oops. Just to show you that everything that I've written down here has an exact analog on here. So when I say something like the derivative of the function f, that's this f with a prime marker here. When I say evaluated at x equals a, I'm saying my input is equal to a. Is equal to, that's the equal sign on there. And then the slope of the line tangent to the curve y equals f of x where x equals a. Usually we use m for that slope. Okay. I want to talk a little bit about, now that we've seen kind of what the derivative is or what it looks like on the graph, I want to show you some uses for it and just kind of where we're going with this in the chapter. I would say the examples that we come up with for how you're going to use this as an architect are a little contrived. You know, they do relate to something that you could do. For example, there's a problem that we'll see where you have a window that is designed like this, where suppose that this part of the window is tinted, so it only lets half of the light through as the top part. So we'll say this is tinted, and then this is clear up here. If you're given certain restrictions on that window, you can figure out sort of the optimal dimensions of that window under certain constraints that's going to let the maximum amount of light through. So we will look at examples like that where I'm taking the ideas of calculus and applying it to you know, things that happen within the umbrella of architecture. But the technique that I'm going to show you that will probably have it's the most likely to actually impact your work and something that you could actually do in a job scenario is something called optimization. If you think about, and this is, we'll be going over a lot more complicated scenarios than this, where we actually have realistic restrictions on things. But if you think about all of the Nobel Prizes that have been awarded, not for things like peace or for poetry, but if you think about the Nobel Prizes in science, you know, physics, chemistry, economics, I certainly don't understand hardly any of them. There's maybe two that I feel like I actually have a grasp on, but you are able to, in this class, we'll kind of explore a Nobel Nobel Economics Prize winning idea. And I'm going to do a very simplified version of it without any restrictions on it, but it uses the derivative. Let's say that you are working at the butter factory and the output here is your profit. If you don't sell any butter, then you don't make profit. But then at a certain point, if you sell, for example, this amount of butter, right? And I'll label with A here, then that's the maximum profit. After that, maybe it's just too expensive to maintain that many cows, or you have to hire extra employees, and it's just not worth it. But what's happening mathematically at that point is that if this is your function y equals f of x here, or $ equals f of x here, that f prime evaluated at a is equal to 0. That happens when you have maximums and minimums of your curve. Clearly here I can see the maximum, I can just point it out, but regardless of how complicated your function is, your maximums and minimums are going to have that same quality. So we're going to spend a lot of time thinking about where the derivative is equal to 0 as a way of minimizing or maximizing things. I'll say this. When I was working at a laboratory, there were a lot of people there that graduated. They had engineering degrees from University of Michigan. It's a good school, all right? And if this scenario, so outside of the context of a calculus class, these very bright engineering degree holding people, if this scenario was presented to them, they would not think to take a derivative and set it equal to 0, right? So at a company, if you've got 100 people working there, I would say 90 of them are, even if they studied calculus and they took Calc 1, 2, 3, differential equations, all that stuff. If you've got 100 people at a company, even if it's very tech oriented, only about 10 of them are going to think to use something like this. If you can be one of those 10 people, you get to take longer lunches, you get paid more, right? You become valuable to the team. You know, this kind of stuff comes up more often than you think. Usually the problem is not understanding how to take a derivative. Mostly it's just kind of recognizing these scenarios. So anyway, even if you're not interested in, you know, you just want to draw pictures, you don't care about any of the technical aspects of it. I do want you to be able to have higher scientific literacy. Are we still in a pandemic? Is that okay? I think we are technically. We're still in the midst of a pandemic. If you remember in the beginning, they talked about flattening the curve, right? It was like experts agree, scientists say that we should flatten a curve, right? And that curve that they were talking about looked something like this. And that curve represented, so that was this I over time, where I is the number of infected people. Right, and the CDC gave their recommendation that they do with any contagious disease. Like this model is part of the SIR model that's existed, you know, long before COVID to model infectious diseases. But actually, I'm going to draw it just one more time. Just make sure I'm illustrating this point properly. So it looks maybe something like that. And maybe about, I think it was maybe about 6 months after the lockdown had happened. We weren't really sure how long it was going to last, but I saw the headline that said something like the rate of infection is finally decreasing, right? We were all kind of, we were over it by, you know, month 4, right? But it said the rate of infection is finally decreasing. So I'm gonna actually draw this just a little bit lighter here. So we'll label these points. So when you saw this headline, rate of infection is finally decreasing, where do you think we are on that curve? What letter would you say? A lot of people kind of put themselves at like somewhere between F or H. I bet if you polled Americans, that's kind of where they thought we were. So they figured, okay, it's been 8 months, so we've got 8 more months and then it'll be done, right? And nobody will have COVID anymore. It'll be very rare cases. Maybe F is just kind of like, okay, we're at the halfway point. Now we're decreasing on here. This phrase, and I understand why this headline came out. We're all looking for some good news. That's at D, right? I is measuring the number of infected people. The rate of infection, which is what they were measuring, that's the derivative. That's the slope of the tangent line. So if you look between D and E, it went from being severe to a little less severe of a slope going up. All right. So I think just in the same way that it's good to know percentages so that you can read an article and kind of understand what's going on with the headline. I think that this was something that I wish more people knew, right? When they see the word rate, to hold that up against, the actual amount that's happening on there. So anyway, we'll have a better understanding of what rates mean by the end of this chapter. You have a quiz due on Friday. What I'm going to make tonight is I've got a list of examples here from quiz 6. I know some people like to get started with the quiz early. So what I'm going to do is just go through each and every one of these examples on quiz 6. I'll put that video up. And then on Thursday in class, we'll talk about theory. But if you want to get started on the quiz, you'll have worked through examples so you can kind of get practice with those. But that's all I've got. So I will see you on Thursday.